Let's think about these two vectors, vector A and vector B. And what I want to calculate is, what this video is about, is our projections, There's going to be two kinds of projections, a scalar projection and a vector projection. Now basically they're the same thing, or at least the magnitude of the vector projection is the scalar projection. Or the vector projection is just a scalar projection multiplied by a unit vector. So the only difference between the two is one is a vector, the vector projection, and one is a scalar, just a number. Now what does it mean? Well, let's take a look at here. I've got vector A and I'm going to do my projections on A. The angle between them, I put them tail to tail. The angle between them is theta. And I'm going to think about if I'm shining a light down on B, the projection of. So that would be dot, 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 making a right angle here. And when I'm talking about the length of this line here, that's supposed to be that's how long this is supposed to be. For some reason I write on an angle. But anyway, how long is this line? If we were going to just use regular, we weren't in any kind of we're just going to use regular trig, then I know how long this vector is, magnitude of B, so I know what this one is from regular plane trigonometry. I guess I should have just kept that red. That the length of this line is the magnitude of B cosine of the angle between them. That's how long this is. And that's actually then, this what I've written in red is, that's the cos of the angle. What I've written in red here is the scalar projection of B on A. So there's no symmetry here, right? B on A on B, they're different things. So I'm projecting on A. And so far this looks pretty straightforward. We're going to use the idea of a dot product then. Now, things I know. I know that if I take the dot product of two vectors, I get magnitude of A, magnitude of B, cosine of the angle between them. That's one of the expressions for a dot product. Get the number. So this is, well, I've got a piece of that right here. And so if I were to, multiply this by magnitude of A, so let's think about that. So this is that's the scalar projection. But if I were to multiply top and bottom here by magnitude of A, then the expression I've got here, the top can be equal to A dot B. And if I have vectors in component wise, calculating A dot B is easy. Divided by the magnitude of A. So this is another way to calculate the scalar component. And if I wanted it to be a vector component, then I want it to be this long. So now I'm talking about this length here, but in the direction of A. So since I can move vectors around, let's think about, I'm now talking about not this length, but I'm trying to make it parallel to that other red line, that vector. So I already know how long the vector is, I just have to give it a direction. So to give it a direction, I want it to be in the direction of A. So I need to multiply it by a unit vector in the direction of A. Well, I'll take A and divide it by its magnitude. So this piece, I will circle it, that is a unit vector in the direction of A. So now what I've got here written is the vector projection. So what was the difference? I took the scalar projection, the number, and I multiplied it by this unit vector to make it a vector projection. And now we can clean this up a little bit, right? Because I've got A dot B, and this would be magnitude of A times magnitude of A. That's magnitude of A squared, and I know that that's A dot A. So this expression, that expression can be, or is, a way to calculate component-wise the vector projection of B on A. So let's go and see where we're at now with the, okay, back to the actual writing part. Two kinds of projections, the vector and the scalar. We saw what they mean. The differences in the unit vector. Here's our scalar projection then, our component of B on A. The little subscript here, that little subscript is saying what the direction is. So A dot B divided by the magnitude of A. Here's our projection, our vector projection. So let's be careful when we're answering questions about, when it says something projection. They're basically the same idea, except one has a direction to it. But I don't get full marks if I answer the wrong one. If it says vector projection, I only give the scalar projection. So pay attention to what they're actually asking for. Some books, some people will just say, what's the projection? That's unclear. And so I think if someone just said, what's the projection, if I couldn't ask them, do you want the scalar or do you want the vector? Then I would give them the vector one if they were unclear. Let's do an example. So here's a projection. There's A and B. So I want to calculate, let's calculate, okay, both projections. By both projections, I mean the vector and the scalar projection. So let's look at the component or the scalar projection. So I need A dot B. So I'm just going to take the dot product of these two. First component times first component, 0 times 1, plus 2 times 1, plus 3 times minus 2, 3 times minus 2, minus 6. And now I need to divide it by the magnitude of A. The magnitude of A is the square root of first component squared plus second component squared plus third component squared. And when I simplify this, minus 4 over, when I simplify this, I'm going to get minus 4 over root 14. There's the component. That's how long that line was, that red line on the bottom. Now let's look at the vector projection. Now it says vector projection, or it just says projection. So I'm going to get an actual vector for this. So the answer here is a scalar for the scalar projection, or just a component. The answer for the vector projection is going to be a vector. So I can copy paste because the A dot B is the same. First times first plus second times second plus third times third. But the piece underneath is magnitude of A squared, but that's really A dot A. So we could even write that as A dot A, and sometimes that's maybe nicer. Magnitude of A squared, A dot A. So that'll be first times first plus second times second plus third times third. That's our 14. Now this is all times the vector. So when I clean this up, this is going to be minus 4 over 14, but I should multiply that through the vector. So our scalar component is minus 4 divided by 14. I should multiply it through, so my vector is going to be minus 4 divided by 14 minus 8 divided by 14 and minus 12 divided by 14. This would be our vector projection. That's the vector that B projects down onto A, like from our drawing. But now remember that it's different, right? The subscript is the direction. So projection of B on A. So it should always be in the direction. Your answer should be parallel to A. And it is. It's just minus 4 divided by 14 times that. And yeah, we can do some simplifying here if we want to. So there's our idea of our two projections. If you think about this from physics, then We would break like velocity vectors up into, a horizontal component and a vertical component. It's the same idea, but we're keeping the actual direction. We're not just telling you we're not just telling you the magnitude. Well, unless we're talking about scalar projections, and then yeah, we are talking about the magnitude. So there's our both kind of projections. Different then, I get a different answer if I do, here I've done B on A. If I did A on B, the direction would be different. It would be parallel to 0, 1, minus 2. Our denominator here would be different. There's our idea of projections. We're finding out, if I wanted to describe what a projection is in words, it's how much vector B points in the direction of vector A. And it's either how much, like just a number, that much magnitude, or it's how much as a vector, magnitude plus that direction.